Okay, the final topic that we want to discuss this week is called inverse of a matrix. I think you may have seen this before, but I want to recap the key terminology with you. Firstly, I want to remind you what are identity matrix. So identity matrix. So for example, what do I mean by I2? I2 means a 2 by 2 matrix such that you have 1, 1 at the diagonal and all the remaining entries are 0. And what's I3? I3 means all the diagonal entries are 1 and all the other entries are 0. And it's a 3 by 3 matrix. That's why we call it I3. And then you probably can imagine what is IN. IN is a n by n matrix, okay, n by n, such that all the diagonal entries are 1, 1, 1, 1, 1, 1, okay, and all the off diagonal entries are 0. So you get 0, 0, 0 everywhere else, okay? Let me just draw back 0, okay? And what's so special about this identity matrix is that in doing multiplication, so if A is an n by n matrix, then A times IN equals to A. And then also IN times A equals to A. So IN is like, so let me write it, it's like 1, 1 in ordinary multiplication. So when you have identity matrix, multiply to any matrix else, nothing happened. You get back to A, okay? And then so it looks like a 1, okay? But then in matrix theory, we don't call it 1, we call it identity matrix. And then what's inverse matrix? Inverse matrix extend the concept of identity matrix because identity matrix we look like 1. And then what's inverse? Inverse means I want to find a matrix such that when you multiply to A, you get 1. Okay? So it's like when you were younger, so in baby mathematics, the inverse of A, of a number A, is A to the minus 1, right? Because when you multiply these two numbers together, you get 1. And then in matrix theory, when you have a matrix multiplied by some matrix, then you get identity matrix, then we call that matrix to be the inverse matrix, okay? So this is the definition. So let me give you some concrete example. For example, so example 1, if A is 1, 2, 3, 4, then what is A inverse? Then A inverse turn out to be minus 2, 1, 3 over 2, and minus a half, okay? Minus a half. If you do not believe that, you should check, okay? Check yourself. A times A inverse is indeed the identity matrix. In this case, the 2 by 2 identity matrix, 1, 0, 0, 1. So check yourself, okay? But you need to be careful about not all the time matrix have an inverse. So for example, if A is 0, 1, 0, 0, then you realize that A times any other matrix, A times any matrix A, B, C, D, what you will get is CD 0, 0. So you realize that no matter what matrix you put here, you can never make this, so this is never the identity matrix. Because this entry is never 1. Therefore, in this case, the inverse of A does not exist. So this is a different phenomenon from numbers, because numbers, as long as you have a non-zero number, you can talk about what is inverse. However, in matrix theory, even you have a non-zero matrix, the inverse can or may not exist, okay? And then in the next theorem, we give you a criterion and the method to find inverse of a matrix. So let us look at theorem 10.5.1. Okay? So what does it say? So let A be a square matrix. So firstly, about existence. When does inverse exist? Inverse exists, it turns out it's equivalent. So I mentioned that if and only if means equivalent to, okay? Equivalent to the determinant is not 0. So for example, this one, instead of checking this, okay, you can just compute the determinant of A. So another argument, alternatively, because in this case, the determinant of A is AD minus BC, so this is 0. So we also know that from this, we know that A inverse does not exist. Alright, so this is how you determine whether inverse exists by computing the determinant of A. But the more interesting part is the second part. That is how to find the inverse of a matrix. So the way to do it is to by Gaussian elimination. So let me write it down. So how to find inverse? Of a matrix. So it's kind of funny. It's not obvious why this works, but then again, because this is not a free theory course, so I can't go through the theory with you. Otherwise, it would take a few weeks to go through it. Okay, but how do we find it? By Gaussian elimination. So suppose I have a matrix A. I want to find A inverse. How do I do that? So firstly, I insert an identity matrix next to it. And then I try to use Gaussian elimination to transform this matrix, into the form identity on the left-hand side. And then what do I get on the right? What you get on the right, this would be A inverse. Okay? So this is a very interesting way to find inverse of a matrix. As I say, it's not obvious why this works, okay? But again, I will demonstrate that with an example. So example, compute the inverse of this matrix. So how do we do that? Firstly, I copy down this matrix. 1, 2, 1, 0, 1, 3, 2, 4, minus 1. So let me give you a name. So for example, I call this A. The method is I insert an identity matrix next to it. So I insert 1, 0, 0, 0, 1, 0, 0, 0, 1 next to it. So this is what I call A, and then with identity I3 next to it. And then what I'm going to do is to use row operation, Gaussian elimination. So after many steps, I hope that the left-hand side would become an identity matrix, okay? And then whatever junk I have on the right would be my inverse matrix. So let's do it carefully. So we want to transform this into the identity matrix. So we do the Gaussian elimination. So the first guy we want to kill is this 2 here. So what I'm going to do is to multiply the first row by -2 and add it to the third row. Then I will get 1, 2, 1, 1, 0, 0. So this 2 unchanged. And then multiply this by -2. And then add it to the third row. Then I get 0, 0, okay, -2, so I get -3. And then -2, and then 0, 1, okay? So good. Okay, next. So I want to transform this into identity matrix. So I want to make this become 1. So I'm going to divide or multiply, okay? Multiply the entire row by -1/3. So I'm going to multiply the entire row by minus 1/3. Then what I get is 1 to 1. 1, 0, 0, 0, 1, 3. These are unchanged. The only thing that I change is 0, 0, 1 minus 1/3. So 2 over 3, 0 minus 1/3. Okay? Although this is in whole echelon form, but this is not the end because this is not identity matrix yet. So we have to do further. So what we're going to do is we want to make these 3 entries become 0. Then I will get an identity matrix. So let me kill this 2 first, okay? Because I can use this 1 to kill the 3 and kill the 1 here. So, for example, so this is unchanged. And then I'm going to multiply the 3rd row by minus 3 and add it to the 2nd row. So I'm going to multiply the 3rd row by minus 3 and add it to the 2nd row. Then what I will get is 0, 1, 0. And then multiply this by minus 3. So I get minus 2, add 0, so minus 2. And then 1, and then minus 3, so you get 1 here. Okay? And then also I want to kill this 1 here. So I'm going to multiply the 3rd row by minus 1 and add it to the 1st row. Then what I get is 1, 2, 0. And then multiply this by minus 1 and then add it to the 1st row. So multiply this by minus 1, add it to the 1st row. You get 1/3 and then 0 and then 1/3. Okay? So this looks very similar to identity matrix, but then we're 1 step off. We need to kill this, okay? How do we kill this? We use the 1 here. We multiply this by minus 2 and add it to the 1st row. So we multiply the 2nd row by minus 2 and add it to the 1st row. Then I will get, so I get 0, 0, 1, 0, 1, 0. These are unchanged. Okay, and then I get 1, 0, 0, and then multiply this by minus 2, then add 2, you get 0. Multiply this by minus 2, you get 4 plus 1 over 3. So let me write down 4 plus 1 over 3. And then multiply this by minus 2, add it to 0, so you get minus 2. And then finally, minus 2 plus 1 over 3. And then you say, oh, great, okay, great, because this is the identity matrix. Therefore, according to our algorithm, whatever you have on the right-hand side is the inverse matrix, okay? So this would be the inverse matrix. So hence, A inverse turns out to be the matrix, okay? So let us compute the entry. So this is 13 over 3. And then minus 2. And then minus 5 over 3. And the other I just copy. Minus 2, 1, 1. 2 over 3, 0, minus over 3. And we are done. Okay? We are done.